The universe is a vast and mysterious place. We've always looked up at the stars and wondered about our place in the cosmos. But what if I told you that the most profound mysteries aren't light years away, but actually hidden within the very fabric of reality itself? What if the universe isn't a giant clockwork machine, but a realm of endless possibilities governed by the strange and honestly pretty counterintuitive laws of quantum mechanics? Welcome to the quantum revolution, a journey into the heart of matter, where the familiar rules of physics break down, and a universe of wonder really does await. This is not just a revolution in science, but a revolution in how we understand the very nature of reality itself. It's a revolution that's already shaping our future in profound ways. This revolution isn't new. It began over a century ago with scientists like Max Planck, Albert Einstein, and Niels Bohr. These pioneers dared to imagine a world beyond our everyday experience, a world where media group, close-up of energy packets in a particle simulation, quantum dots under microscope at its stock at a distribute underscore equally. Energy isn't continuous, but comes in discrete packets called quanta, where light behaves as both a wave and a particle, and where the act of observation can actually alter the very fabric of reality. So, join me as we embark on an adventure to explore this strange and wonderful world, to unravel the mysteries of the quantum revolution, and to discover just how it's shaping our future. Our journey begins at the dawn of the 20th century. Classical physics, with its neat and predictable laws, totally reigned supreme. Isaac Newton's laws of motion explained the movement of planets and stars. James Clerk Maxwell's equations described the behavior of light as electromagnetic waves. The universe, it seemed, was a giant clockwork machine, its future predetermined by the laws of physics. However, cracks began to appear in this seemingly perfect edifice. Scientists struggled to explain the strange behavior of light. Experiments showed that light, when shown on certain metals, could knock electrons loose, a phenomenon called the photoelectric effect. This just couldn't be explained by the classical wave theory of light. Enter Albert Einstein, a young patent clerk with a revolutionary idea. In 1905, Einstein proposed that light, in addition to its wave-like nature, could also behave as if it were made up of tiny packets of energy called photons. This radical idea, which earned him the Nobel Prize in Physics in 1921, laid the foundation for the quantum revolution. Einstein's work was just the beginning. Niels Bohr, another giant of 20th century physics, developed a model of the atom where electrons could only exist in specific energy levels, totally challenging the classical view of electrons orbiting the nucleus like planets around the sun. These early pioneers were like explorers charting a new and uncharted territory, the strange and wonderful world of quantum mechanics. Quantum mechanics is the branch of physics that governs the behavior of matter at the atomic and subatomic levels. It's a world where energy, momentum, and other physical quantities are quantized, meaning they can only exist in discrete values. Imagine a staircase where you can only stand on the steps, not in between. That's quantization. This is a radical departure from the classical world where these quantities are continuous and can take on any value. It's kind of like discovering that the smooth, continuous surface of a table is actually made up of tiny, discrete pixels when you zoom in close enough. One of the most mind-bending aspects of quantum mechanics is wave-particle duality. This principle, first proposed for light, states that particles like electrons can also exhibit wave-like behavior, and vice versa. Imagine a basketball suddenly behaving like ripples in a pond, or a sound wave morphing into a tiny solid ball. That's wave-particle duality in a nutshell. Quantum mechanics provides the framework for understanding the behavior of atoms, molecules, and the fundamental building blocks of matter. It's a bizarre and counterintuitive world, but, it's the world we live in. One of the most intriguing and mind-boggling phenomena in quantum mechanics is entanglement. Imagine for a moment two particles separated by a vast distance, maybe even light years apart, yet they are linked in a way that totally defies our everyday experience. When we measure the state of one particle, we instantly know the state of the other, no matter how far apart they are. It's kind of like having two coins flipped at the exact same time, even though they're miles apart. If one coin lands on heads, you instantly know the other has landed on tails, and vice versa. This spooky action at a distance, as Einstein famously called it, suggests a connection between entangled particles that actually transcends space and time. Entanglement is not just a theoretical curiosity. It has profound implications for our understanding of the universe, and it's at the heart of many emerging quantum technologies, including quantum computing and quantum cryptography. Another cornerstone of quantum mechanics is the uncertainty principle, formulated by Werner Heisenberg. This principle states that there are fundamental limits to what we can know about a particle's properties. For example, the more precisely we know a particle's position, the less precisely we can know its momentum, and vice versa. Imagine trying to pinpoint the exact location and speed of a firefly buzzing around in the dark. The more you focus on its position, the less you can track its speed, and vice versa. And this is not due to any limitation of our measuring devices but a fundamental property of nature itself. The uncertainty principle has profound implications for our understanding of the universe. It tells us that the universe is not deterministic but inherently probabilistic. We cannot predict the future with absolute certainty, only the probabilities of different outcomes.